Hello, I'm one of the researchers on the COINVENT project. The COINVENT project is a European funded project which is intended to try and discover some of the ways in which computational creativity can be automated. And we are particularly interested in mathematics and music. The way that we go ahead with our research is to use a framework known as category theory to try and explain the meta-theory behind how new concepts can be invented, and indeed how one might be able to take theories in mathematics to be creative about how one creates new theories, or concepts from music and be creative about how one finds new concepts in music, or indeed blend the two together. And blending is a word which is used very often in this project, and it's used to try and describe how it is that concepts can be fused together into something new. And in particular we're trying to find ways of automating this sort of creativity. So we're going to show you some examples of the software working, and the first example that's going to be on there is an example from music where one tries to blend cadences. So cadences are generally two chords, so for example one might take a perfect cadence as being G7 to C major, or another cadence known as the Phrygian cadence as B flat minor to C major. Now, what is interesting here is you might want to try and take these two concepts from different idioms of how cadences are created and to try and find a new cadence. And so, as the software will show, and we show the demonstration of the software, one of the things you can do with this is to try and blend these two together and to try and weaken out some of the concepts of them to get a new idiom for a cadence, and that being something from jazz known as the tritone cadence, which can be played like this, which is something you find very often. You'll notice I added a major seventh in there, and that's often referred to as completing the blend. So this is something which is pervasive in most of jazz. So if we take a perfect cadence, for example, in jazz you often hear what's known as a 2-5-1, and you use this notion of a tritone cadence instead. So you often hear that sort of thing in jazz. So the COINVENT project and the software behind it has been used to try and automate this process, and in particular the category theory that lies behind the software has done this. Another example of that from music, if we take another example of music, if I take the jazz tune, the well-known jazz tune, All the Things You Are, which is, for those who don't know it, there is an interesting thing that can be done, which is to try and take sections of the piece which are in different tonal centres and try and work out how one might be able to find joining chords. So at one point in the piece the tonal centre is E major, which is followed by a tonal centre in F minor, and one wants to know how one might be able to join these two things together. So again we'll put in the software here showing what happens, and the software will come up with some way of trying to blend these two chords together to come up with a joining chord. And the chord it comes up with, interestingly enough, is known as a C7 sharp 9 flat 13, and in fact the chord in the real book which is suggested is a whole tone chord, which is C plus 7, which is normally played like this. So you would join the two chords together like this. But the chord suggested, which is very interesting by the COINVENT machinery, is this slightly more rich chord, which is, so when you join the two together it is in fact, and that is what's known as an altered chord. So it's quite nice that it has a theoretical understanding from having been automatically created in the system. It's quite nice that it has a theoretical backing. So the altered scale in C is, and often this is used when you transition from one chord centre to another. So for example, in this case, which is a very common thing to do. So if we now move on to some other examples from mathematics, as the software will show, some of the examples are really very complicated mathematics, so they're harder to show on a piano. But the first example is one where I blend the concept of natural numbers with lists to try and come up with some what are known as eureka lemmas. So mathematicians come up with clever theorems to try and allow them to prove theorems and compartmentalise the way in which proofs are done. And the second example is one from a much more complicated area of mathematics, which is the prime ideals, the ideals, the theory of ideals and the theory of primes. And again, we've got some quite interesting results there, and you'll see the demonstration of that. So opening up the COINVENT software, I'm first going to open a G7 chord specification corresponding to a perfect cadence onto C, and then a B flat minor, which corresponds to a Phrygian cadence in C. The first thing I'm going to do is to tell the system that we're working with cadences, and I'm going to remove the weakening to show you what will happen without weakening. When we compute the blend without weakening, what happens is instead of having a G7 onto C and a B flat minor onto C, we in fact get this very strange chord, which is not something that we want. So what we're going to do, if I just show you this in Hertz, first of all, without weakening, we have no weakening. There's a classic push out from the category theory. So now we're going to apply weakening in amalgams, using amalgams to compute the generic space, and the weakening scheme will be removing some axioms and compute the blend. So I'm going to use the results I've already computed before to show you the blend. The first thing that happens is it asks me for a root to complete the blend, and I can use some other software to compute that and Markov chains models we have. And the blend now sounds like this. And if we look at it in Hertz, you'll see that the 3/2 co-limit type of theory, where each of the input theories G7 and B flat minor has been weakened to create the push out. So this is the example. So this is another example now taken from maths and specifically theorem proving. So first of all, I'm going to take a theory of natural numbers, and secondly I'm going to take a theory of lists. The idea here is we should be able to transfer knowledge from one theory to the other. Specifically, we have this theorem, fact equals q fact x0. That's a theorem. In order to prove that, we need this eureka lemma. And I want to be able to try and reproduce that eureka lemma for a similar theorem in the list theory. So in weakening, I'm going to use a weakening scheme of removing axioms and also of adding and removing arguments. And I'm going to call the amalgam system to do this. This takes some time, so I'm going to use previously cached results. And if we look at the results, we can see that this eureka lemma has been generated at the bottom, app rev x, y equals q rev x, y, and this is a lemma which needed to be created. It's a creative lemma, it's a eureka lemma, and it's analogous to the one in the naturals theory, and we use blending and weakening to find that. We have some results of that, and if you show this theory in Hertz, you can see how the input theories of nat and list have been weakened onto other theories to find a blend which is consistent and finds the eureka lemma. So in the COINVENT system, it's possible to add certain theories to a sort of batch process, which is called managed group theory. And now here, for example, I can add some group theoretic notions of cyclicity and identity, some more what's known as image schema type stuff to do with rotation and to do with binary operations or magnitudes. And what we can do is we can choose how the weakening schemes and the programs we want to use for calculating generic space and so on, and we can run this. This takes some time, but as an example, here's an example that we ran and created in Hertz, and this is combining various notions of magnitude, the number line, rotation by 180 degrees, for example, to combine with the naturals to give you essentially a theory of the integers, which is a theory of the integers which still requires some sorting out, but it is nonetheless a consistent theory of the integers. It's quite difficult to see that, of course, but after some searching, this batch mechanism can produce such results. As a final bit of experimentation, we've been experimenting with the ideas of 2D and 1D cellular automata with locally defined rules, which we can define in any semantics. Here the rules are defined via partitions, by a theory of partitions, and we allow the propagation to happen via blending, via the notions of blending that we have.
As you can see by this interesting little simulation, each of the cells has a different sort of property, and that's blended with its others when it's alive. So this is a bit like the Conway game of life, except that the results are that we have locally blended rules. It's not just alive or dead. The replication info, as we call it, which is blended as a blend of the mathematical theories underneath. And there's various operations you can choose, there's various ways in which blending can happen, and this all corresponds to the blending that you saw earlier in the overall system for COINVENT.